Hey everyone, this is Dr. Walker. In this video 514, we're going to talk about electric flux again, but we're going to look at a more general case. In the previous video, we were only considering flux when the field was uniform and the area was flat. So in this video, we're going to look at curved surfaces and non-uniform fields. How do we calculate the flux in this case? So what we do is we're going to look at a small patch, a small area patch on this surface. And this happens to be an open surface. It's not a closed surface. We'll do closed surfaces on the next slide. So if we want to find a flux here through this small patch, then because the patch is really small, then we can consider this area segment to be approximately flat, and we can consider the electric field to be approximately constant. So we can use a definition of flux that we just learned about, which is the electric flux. So just for this little I segment here, is going to be EI dot delta AI. But now we want the flux through the entire surface, so we need to sum up the contribution of all of these patches. So the electric flux is approximately going to be equal to the sum of all of these patches, so all of the EIs dot delta AIs from I equals 1 through n, just sum up all of the contributions. But in order to get an exact result for electric flux, we need to consider the limit, right? The limiting case where these area elements become infinitesimally small and we have an infinite number of them. So as we take that limit of the sum, that is how we get our surface integral E dot dA. This is a more exact answer to find the electric flux through a surface where the field may not be uniform, the area may not be flat. The units for flux is still the same, newtons meters squared per coulomb. We can also generalize this to a closed surface. The integral is going to look the same. The only difference is that we now have a circle through the integral sign to specify that this is a closed surface rather than an open surface. But in either case, we have to integrate over the entire surface in question. And then a quick note about whether flux is positive or negative. And I kind of assumed this in the previous example where we were looking at the cube. If you remember that guided example in the previous video, and I drew this area vector here. And the reason I drew it outward is because I was already thinking about the closed surface. But if it's just an open surface, then I could have drawn the A either going up or going down, right? But the convention for closed surfaces is always to have that area vector going outward from the surface. So in that case, if the electric field is also leaving the surface, then the angle between dA and E is going to be less than 90 degrees, and the cosine of that angle is going to be positive. So we're going to get positive flux for the field leaving the surface. But when the field is entering the surface, then we're going to get negative flux. Because now the angle is greater than 90, less than 180, that's going to be a negative flux. So I just made that note here just to remind us of the sign conventions. Positive flux when field is exiting, negative flux when the field is entering that surface. Let's look at one example here. A point charge is located at the center of a spherical surface. Let's draw that spherical surface. The radius of the sphere is halved. So let's draw a smaller surface with half the radius. And it says what happens to the flux through the sphere now that it's halved. So pause the video, think about it for a second. Okay, so you may be thinking, well, it's a smaller surface, so our flux decreased because the flux depends on E and A. However, remember, the main idea of electric flux is that it is a measure of the number of lines that are penetrating the surface. So if you think about the electric field produced by this point charge, you can see that there is just as many lines going through the small area as the big area. So the flux is actually the same through both. And if you're still thinking about, well, what about the fact that this area was smaller? Well, remember also that the field, when you're stronger to a charge, the field is stronger than when you're further away. So the smaller area gets balanced out by the stronger field. You still have the same flux throughout. So it's better to think about the number of lines penetrating that surface to get an idea of the flux. And we will do another example of electric flux in the guided example video that follows.